there's something like a stove. So what we have here is this conversion factor, and you see all the calibration we made, actually not real code calibration, that's representative number of the calibration we made. For the alien sensitivity must become along the experiment. You see there is no kind of evidence, which is good. And the average value is 63 converter per ppb. And also the linearity is quite good because here, well, I didn't distinguish actually in this plot, but we have here amount where admitted between ppb level and ppm level, we have a factor of 1,000. And the average, well, the constant, the factor, conversion factor varied between 63 and 55, 56 or 67 and 58, something like that. So what you have here is also a representation of the good linearity in that range of the amount of medium considered. So with this sensitivity, one can draw this red line, which is our detection limit. Actually, in the actual condition of the experiment, the mass spectrometer had a high intensity detection limit about 1 picoampere, which is not the sensitivity, the limit of the mass spectrometer itself in that particular condition. And you see this goes down to 0.03, something like that, ppb helium, or an absolute number in the order of some 10 to 11 atoms of helium, or 10 to minus 9 cubic centimeters of pressure condition. Actually, this is a slightly extrapolated limit because we did not consistently make handling of where samples below 15 microliters. So this is actually a slightly extrapolated limit, something like from here to here. Now, coming to the results, here are the same results of what we showed you yesterday. Let me say before that we do have I will try as much as possible to move around the so helium world today. I will try to look at the internal consistency of the data and without any reference to the other evidence or problems that Gersi showed you yesterday. So we have cell number 4 and cell number 10 here today because these are the two cells for which we have the most significant results. And you, looking at this result, you can have an immediate appreciation that after, let's say, in the final version of the experiment, we had quite large values to helium measure. Now, about 900 hours, we had to make a mechanical adjustment of some of the assembly, cell assembly, and so we were very, we suspected that something would have occurred to the tightness of our collecting lines. How to confirm or prove or deny this hypothesis? The only possibility for us was to look at the reference cell. Of course, it's not really the proof about that because the reference cell that occurred something to the reference cell and not to the other one or vice versa. we really have here a build-up of the helium measured, let's say, for the cell 4, also in respect to the background measured before the beginning of the experiment, or, let's say, parallel length we have, which is the reference cell number 1. Now, looking at the cell number 10, red is number 10, green is always the reference cell. Please take notice that we have here a quite different scale. All the block before was within 100 ppb, we are here in the 600 ppb scale. And unfortunately, we do not have for cell number 10, which was supposed to be of poor quality, the line in itself and also the cell. At least, in my opinion, was the cell for some less quality. We do not have a background before the beginning of the experiment. We say also that some of the problem we have in this experiment is because we have to share, of course, our mass spectrometer with the other ongoing program. So, as I am in charge of the mass spectrometer session, I must say that it was my fault. I was late in having the mass spectrometer at the maximum sensitivity, so I was late in giving all the inputs to the other people. However, since the very beginning, we have to quite high with respect to the other. So, signal being measured in the order of 60 ppb or something like that. And what I thought that time was that we were following a leaking lines on which, however, we could have the possibility to look at some rate increase in the helium content. Actually, it occurred some increase here, and suddenly, shortly before 600 hours, we had a big peak, and the helium intensity went down to the background. So, what to think about? Well, that moment we were confronted with the possibility that we really would have leaks opening and closing, or we were really observing some interactive phenomena since the very beginning. So we posed ourselves the question how to check if we have inadequate information. Up to that moment, we were basically looking at the helium, hunting for helium, looking at the background, waiting for something occurring about the background, and that was all. But here we had to devise some way in order to check if the air leakage hypothesis was confirmed or not. Now, helium was selected because of the only component of air is the only one which is not condensed in the power vacuum of the amount. Before going on, let me show you all the other cells. And the reason why I'm not focusing on these cells is that we do have for some 278 loose points, values that are in the range of the reference of the blank cell. So I will not comment on that much. Just to fix the idea, I will be reproducing all the data, our data for green line, cell number 1, reference, blue, 4, and 10, the red one. So you see, we have really dramatic decrease of the helium content for cell 10. And so, looking at helium, we had to answer two questions. Was it possible to measure the neon 20 to discriminate between medium 20 and the other masses at 20, nominal mass 20? And was it possible to measure both helium and neon always simultaneously? Now let's look at the possibility of the mass we have here. Nominal mass 20, this is really a collection of all the, I would say, also the rings. And most importantly, we have here for sure the ultraviolet water, the oxygen 18 water. Remember that we are speaking about PPD levels, so the substitute for with the oxygen, the natural one is important here. Neon plus and the double united argon, because we were looking at helium at 100 eV, so we have also double united argon. Superimposed, you see also the hour resolution power, and you can look, you can appreciate that we are not really resolving neon and the operated water or water itself, because a slight superposition of these two will give you still separated peaks, but not completely resolved. However, it's of course impossible with this resolution to resolve neon in argon plus, but as argon plus has an appearance potential of 43.4 eV, by working at 40 eV, you can easily take it off your spectrum and look only at neon and look at the possible masses around this point. So, now addressing the second question, was it possible to measure both helium and neon? Once again, we follow the neon time dependence for fairly large different amounts of air and so on, helium and neon, of course, useful. And we saw that there is also a good superposition here. And once again, we could take for the maximum intensity over the interval. I showed that looking at on the same scale, at neon and helium time dependence, you see that is it possible to look at neon, helium, and shortly after having followed the peak, to follow the neon for a very large amount of time in order to be able to get trace to the maximum intensity. We can get trace with good confidence because we have superposition of the neon time dependence in a very large range of values. Now, let's see the actual measurement. It's an example of measurement, of course. It's somewhat less neat than the helium measurement. Here we are on helium. We follow helium just for the time necessary to look at the time dependence, to control that we are on the helium in the background, and to measure the deuterium. After that, we shift to max 20. We lower the ionization energy to 40 eV, and we very slowly scan max 20 magnetically in this case. And so in this case, you see the neon, this typical time dependence goes down, and we can back trace to the maximum intensity down here. To be honest, this is not always the situation. Sometimes we do have better resolution, and sometimes not, because we are following the condition in which we have the water and so on is by no means controlled by us. So in some cases, in which with low amount of neon work, it turns out is that you have only a shoulder of the neon with respect to the larger masses of mass point. Nevertheless, it's my opinion that we can have a fairly good estimate of the neon intensity. But it's also the reason why we approximately doubled the error of neon with respect to the original. Now I am hopefully convincing you that we were capable to measure both helium and neon almost independently. And I should now show you the results. Basically, I was looking at the very beginning at the helium to neon ratio with respect to the air. Quite manually, I would say, but this was my idea at the very beginning. And of course, we got for the set, this is the case of cell number 4. Actually, we began our measurement when the only producing, it's in brackets, cell was cell number 4. And this helium to neon ratio was definitely higher than the air ratio. And it lasted for less than 1 day, the happiness, because when measuring our reference cell, it became apparent that the error measure for the reference cell were in the same range with that of cell number 4. So some fractionation mechanisms that work here. We have a preferential helium flow with respect to neon flow. what's the possible mechanism of this inflow? Well, a very simple possibility is that you have a Knudsen, it's a great tracing of all the data. Now, blue one is the set 4, set 3, set 1. It's a Knudsen mechanism, and you see that the data are neither fully consistent or fully inconsistent with the importance of Knudsen flow inside our apparatus. However, it can also be that we have a combination of mechanisms, but I would like to state very clearly here that it can be, in my opinion, it can be a consequence of the materials. It can be permeation, because that's once again this here. The material used for cell number 1 and 4 are exactly the same. Stainless steel is less for the cell, less for the combiners, and here stainless steel joints are exactly made with the same materials. And also this is true for 2 and 7, 8 and 10. Why? We got helium values for cell number 4 that are approximately 1 order of magnitude in cell number 1, and for cell number 10, something like 2 order or more greater than cell number 2, 7, or 8. So it can be permeation. It must be if there is leaks through the joints or some defects of the materials, but not of the type of materials. So, views were not really good, but not really so bad. But now we are able to learn that news come, because when we have enough data, we could plot helium to neon with respect to neon for all the cells. And it's quite apparent that there is a correlation between the two. So when you get high helium values, you also get high helium values and vice versa. And you see here you can superimpose the Knudsen possibility, and that of course is as before. Neither fully consistent or non-consistent. If you expand, if you go up in the region, the general picture doesn't change. And this is, of course, not really what we look for. Sorry. If you look here, you can think that maybe there is a combination of mechanisms, just airflow helium or Knudsen, or possibly release of helium and inflow with some type of mechanism of combination. Actually, we have I would say, some support to this hypothesis of combination mechanism, because if for the cell number 4, we plot both helium to neon ratio with respect to helium, there is an increase. So if one doesn't think about any helium-assisted inflow, which seems to be really very important, this can be considered support of the production or release of helium from inside and inflow of helium from outside. Now, I will skip this. Now, there really was the possibility that we have leakage. So, if we have leakage, it should be dependent on the amount of helium we have in the air outside the cell estimate. This seems to me that it should be. Actually, we were really very concerned since the very beginning of the possibility of some helium, some increase of the helium content in the air in our department, because in our department is even older. There are MRI machines, there are seismographic work with people, and so we check routinely the quality between brackets of air, but simply by with a device very similar to in the cells area. And by simply comparing these two areas, one could have an estimate of the ppm content in the air surrounding the cell. Now, let's look at this. We have here, with respect to time, the helium measured in cell number 10 and the helium measured in the room surrounding, which is in the air surrounding in the cells room. Of course, the lines here are only a help for the eye. Measurements are at discrete times. But you see here we have a big increase of helium, but no in the air, no increase in the helium measured for the cell. But most significantly here, we were measuring quite closely the helium and the air in the cell. And here we can get one of the most abundant peaks in the helium content of cell number 10. So there is no correlation between the two. This really is not simple to explain by thinking about air inflow in air. It can be, yes, I must say that it can be of interest to you to know that it happens sometimes that we monitoring the helium in air in the masculine room. Not that it happened once, it's actually 15 June. We had a quite large increase of helium in the air from the masculine. We couldn't trace back which was the origin of that, but I'm showing you because it can be helpful to some other people working in the field. One must be really very careful about the content. So let me try to summarize the main point. Against October or February air contamination, we do have results also scanty. I mean, we have possibly two evidence for that show that we do not have correlation between helium found in the cell and the helium concentration in the air surrounding the apparatus. We do have for all the experimental parallel one which do not estimate any deviation from the raw background. And let me say also that, as for myself, spontaneous openings and closing of the helium tanks in absence of any mechanical steps don't seem really my problem. We were very careful of not even touching the apparatus before the particular manipulation until we were at 900 hours. This is quite raw. We have, fortunately, a good correlation between helium and helium. So the simplest explanation, of course, is air. We have helium to numeration that are superimposable for both the cell and the reference one. And as we move the apparatus, we do not have any real proof of a drop to background level after the electrolysis. We can either say that we have or not, or we do not have. So we have to balance different pro and contra. And I am forced to say that stronger evidence, mainly the helium versus this correlation, favors the cause of air contamination. Why that? Because it's the simplest way to explain and think about the helium correlation. However, rigorously, if one sees something that opens and closes contaminant, we are blind with respect to the most important features observed in helium measurement, which were done before the beginning of the helium checks. We could neither validate or unvalidate this measurement. It persists the sample stable helium, I mean, that was I told you, the helium ratio to maintain ratio versus helium cells, which points to a combination of processes, both air contamination and helium release. So I have 1 minute more. I would simply tell you that I should finish show up and didn't show up and so on. And you must know that in Italian, helium, the word for helium is helio, which is the same word we use also for a first name, like Charles, John, and so on. And so I was speaking about this helio and so on, and this helio and so on. And once my little daughter told me, well, Dad, why are you so fond of this guy, Helio, if he is so nasty with you?
Questions? Doug, why don't you go first?
Well, I mean, you have a very nice mass spectrometer there, but I mean, I once spent several months working with helium. Sorry, your mass spectrometer is very nice, but I once spent many months working with helium, and it's incredible how it moves around and goes through seals that you think are solid. But my question is, what about helium-3?
No, we didn't measure helium-3 at all.
But I mean, in experiments on DT fusion, you normally find there's 10 million times more helium-3 than helium-4. So I think it'd be a very nice experiment to do, and your apparatus, your mass spectrometer, is excellent for it.
That's what we do.
Professor Vargas.
Well, there's obviously a tremendous battle about leaks, impurities, and so on in fluorine. Isn't it better just to try to look for helium in the electrode? And many of these difficulties go away. And some work we have done recently looked for helium-3 and helium-4 in the electrode. Helium-4.
Of course, you're right. We have to build some apparatus in order to do that. And once again, it's my fault. I am the high temperature chemist inside the group, and I should be able to just heat up a small piece of metal in order to release helium. But it was also time, but it was not being done.
Now, the helium-4 experiments are very important because helium-4 is the only fusion ash in the observatory now where you might try, but it's still sinking many orders of magnitude too low to explain the excess heat. However, these experiments are very important because I think they can be pushed forward in the following sense. If there is, for example, a new phase of D2+, a high phase that Professor Takahashi and myself and so on have suggested, which might account for the excess heat, with a mass spectrometer, you might be able to detect that the mass of the D2 appearing in your experiments is not exactly the usual mass. There should be a difference of 50 keV. Now, whether the mass spectrometer can be made precise enough to do that is not a question I want to ask you. The second point is this: if there is a new phase of D2+, or H2+, due to some interaction like spin-spin or spin-orbital couplings, then you can expect that some neon formation would appear as a consequence just by combining O16 with D2+. This might be an indication of the existence of a new chemistry. But my question is, can you really tell the exact mass of the D2 plus which you have in D2?
What do you mean with exact mass? What do you mean with exact mass? I assured you that
Which appears in all the books. But, all right.
what I can tell you is that by going from 4538 to approximately 4509, we get the mass. The width of the mass is the order of 1.5, something like that volts. So if it is within this limit, we can...
Meaning, would you see a difference of 50 keV?
50 keV with mass, how much?
Okay, let's move on to another question. I want to take a question from the back, please.
Yes, I was wondering if an analysis of electrodes, if you could ever consider accelerator mass spectroscopy, which would have more sensitivity than your device there to look for helium-3 or helium-4 electrodes using accelerator mass spectroscopy.
Sorry, I think I didn't get absolutely. Sorry.
Have you ever considered using accelerator mass spectroscopy to look at the electrodes?
Yeah, to be honest,
Or even the gases?
what we have is a mass spectrometer operated in the, let's say, vacuum impact source. We can change almost nothing of the mass spectrometer because we have to work with this mass spectrometer on the high temperature.
Yes, I understand that while you're doing what you're doing, but I was just wondering if anyone who does this mass spectroscopy would be, thought it would be fruitful to use accelerator mass spectroscopy to look at electrodes.
I would say that the next attempt was really for sure to build an apparatus absolutely tight. I mean, I would like to vacuum tight apparatus in order to be able to check with the mass spectrometer online what's going on. And after that I will be sure about the risk of them. But I have to comment on that. By purpose I didn't mention the results with the interrogation itself. It may be that was an accident, but as Dr. showed you yesterday, for cell number 10, we had 1-to-1 ratio between exactly the same amount of helium and carbonated conditions. And to tell the truth, at the very beginning, I was thinking about the leakage, and he was, of course, thinking about something that was really going on, because he had all the measurement, and I was doing also only the mass spectrometer measurement. So we were really aligned at the very beginning to each other.
Yeah, I think it's important to.
Let's keep this one short.
Yeah, I think it's important to look at the heat and the helium-4 correlation as well. It's obvious that you've divorced yourself from that with good reason. And in some sense, that gets down to what Douglas Morrison was saying. If you do look at the heat, you are getting it from the helium-4. But to echo what Douglas Morrison said, there's an interesting point about the helium-3. And actually, Talbot, my uncle, suggested this back in 1990, that by looking at the ratio of helium-4 to helium-3, if you were to go out and measure the helium-3, that might be a better indication of whether or not you're actually seeing air contamination or not, especially given the kinetics and the diffusivity. So I would echo what Douglas Morrison said, but for an entirely different reason.
I understand. One is, if I got your point, one has to be able to measure the contamination of helium-3 at the level it has in the air. We do not have such a sensitivity actually. The 10 to minus 6, if I remember, 10 to minus 5 maybe, ratio between helium-3 and helium-4 in the air does prevent us to look at the helium-3 flowing inside our apparatus actually.
We've spent a lot of time looking at the possible helium-4 artifacts. One, of course, is leakage from the air. One, of course, is permeation of the helium from the air into the apparatus. But the one that we found the most difficult to handle, and you may be seeing, is the one that Canada found so many years ago, that glass dissolves within it helium-4 from the air or any exposure to helium. And when hydrogen comes near that glass, the helium is forced out of the glass, the dissolved helium, and you get spurts of helium coming out of the glass whenever hydrogen or deuterium sweeps by the glass. Now, in our experiments where we actually evaporate palladium, so we do look at what's in the electrode, and we've never seen helium-3, but we have occasionally seen helium-4 that we can't explain. Those experiments are much easier than the ones where you're looking at the gas phase like you are. I have to say your experiments are very well done. I think they're beautiful experiments. But you should take a look at deliberately putting in a hydrogen gas by the glass surfaces and watch the helium pour out.
Do you think that the helium also works in the same way? Or do you think that works in the same way or not?
Yes, we did it with deuterium. And what we found is with deuterium, when you get several thousand times more deuterium than the helium-4, then the helium-4 begins to ride on the shoulder of the deuterium peak, and you can get artificially high values of helium-4, but you have to have enormous D2 to helium ratios for that effect to appear.
I understand your point. I don't know from the quantitative point of view, but we do have already such an experience in the sense that I didn't have enough time to tell about, but with a very large difference in the condition of the composition, of the gas inside the lines, we did not observe difference in the cell. God is not yes. So in some sense, I don't know how large is the difference one has to use. We already have this evidence that there is no correlation between the composition of the gas inside the lines and the results we got.
One more question.
To this purpose, I want to answer to the questions posed before. We didn't observe now any change in the helium-4 -20 ratio as a function of the composition of the cell. In fact, we have practically the same result. For example, when we have the electrolysis off or electrolysis on. As you know, the composition itself is completely different because during the electrolysis we have deuterium and oxygen. When electrolysis is off, we have only nitrogen in the cell and some EV water vapor, and we didn't find any difference between these two different situations.
Okay, thank you. The last speaker this morning before the break will be Dale Tuttle. He'll be talking about tritium evolution from various morphologies of clay.
I guess this means I can't move around very much. See, according to schedule, I'm either 20 minutes ahead or 20 minutes behind. I don't know whether to start in the middle of my talk and give the last half, or start at the beginning and give the first half. I do have a slide from the previous speaker. I can try to discuss it. This is the cast of thousands. I don't mean to give the impression that everybody in Los Alamos is working on this project. Although it's a large number of people, it's actually a small amount of time from each one of them. At previous meetings, Tom Plater has given this talk about the work we've done. I think it's going to be a real test today. If any of you know Tom out there, see if Tom can be quiet out there on the podium. If he starts to say anything, throw something at him. I'd like to divide the talk up, start off to talk about the tritium measurement system and the equipment we're using. And then a short review of these palladium and silicon cells, are primarily the ones that Tom has talked about in the past. And then on to some work that we've done in the last year using wire cells, both solid wires and something we started off calling powder wire, which since switched to powder crack. And finally, we're going to have plasma cells. And, if I have time, I'll get into future plans. Just a quick sketch of the region we're working in. We are working with palladium with deuterium gas overpressure. Primarily room temperatures and pressures from 400 torr up to a couple hundred psi. So in stoichiometries from 0.6 up to about 0.72. The tritium measurements we do are the overgas above the palladium, and at the end of the experiment, by heating the palladium up, we drive the residual gas on and also measure the tritium in that gas. This is a picture of the instrument we use, which is simply a 2-liter ionization chamber. It's not a very good picture of the ionization chamber, but it is a good picture of me, so I showed it here. It's at least as good as they get. The ionization chamber is actually a center electrode, which is a fin, not a single electrode, surrounded by a cylinder which is held at about negative 100 volts. The endpoint energy of the tritium decay is 18.6, although the mean is only 5.7. I showed this slide. One of the interesting things up here is the region in which we'll be measuring things is typically nanocuries per liter. Increases in our gas samples of the order a few tens of nanocuries. Nanocurie is 2 times 10 to the 10th atoms of tritium. Given the half-life and the decay rate of the energy of the tritium, concentration in our chamber down in the area we're measuring nanocuries per liter gives an ion current of only 10 to the minus 15 amps. Just a quick look at some calibration curves. We use deuterium gas as our calibration source. Run that against the calibrated chamber and then bring it over and run it in our chamber. We don't dare turn these chambers over to the people who do calibrations at the lab. They'll put far too much tritium in them, and that's all we'll ever see for the rest of the experiment. The system itself is actually requires a little more equipment. It needs a circulation pump and a loop. We actually circulate the deuterium gas around the loop to provide some mixing until it can settle down and get a more constant measure. We do the experiments 2 ways. One is that the cells, and we'll see them later, are actually loaded up in experiments that run off on the other side of the laboratory, or it's BYU or back in the tunnel. Then we bring them back and let an alcohol gas into this loop, measure that, pump that out, let a second alcohol in it, until the pressure is so low that we need to heat the sample up to decompose it to try to remaining tritium. The second way we run them is right at the loop, under continuous flow, so we're measuring the tritium constantly as the experiment is proceeding. I'm going to show some results from both of those types of experiments. If you're looking for tritium levels at this low, there are obviously lots of sources of errors. We're doing our best, and perhaps later on I'll come back to some of these as we go through the results. First is separation effects. Coupled with that is actually the second one, incomplete dehydride. If you don't dehydrate completely the last gas on there in food, it will be rich in deuterium. We avoid that because we essentially pull off all the gas. We see the separation effect. When you sum up all of the aliquots, or you completely dehydrate the sample, that takes care of that. Changes in the ionization efficiency drastic, various gases. We're running deuterium, which is an ionization efficiency of I think around 32 EV per ion there. Air is 34. Methane is 26. It's not a terribly significant change unless you get large amounts of sulfur gas. External environmental changes, we don't have good control of the temperature of our room, and we do see an effect. Internal leakage current is probably one of the biggest ones. We're looking at 10 to minus 15 amp currents. Short-term changes, such as mouth particles or large some ions are coming in, are taken care of by the time. You can see these fluctuations, you see a large increase, and then the change will settle back down to the original value. One of the largest things we've seen is water vapor off the samples. There's metal oxide on, particularly the first cells we run, when the hydride produce water vapor, and that is the chamber. It definitely has an effect. And we'll see some of that later. Next to the last, there's treating contamination in the plating. We're taking fairly great pains in analyzing the treating the plating in various ways to ensure that any treating contamination is below the levels that we're seeing. The last one is treating contamination in equipment. That's primarily a problem in run to run. You get a very good run. You need to spend some time after that cleaning and turning out of the system, or it'll simply appear the next one to give you a bad result. Is there a way to raise this? It's unusual to be as sure as I can do, but mine is too low. We'll start off with plating of silicon cells. You've probably seen this before. It's simply alternating layers of plating. The plating is either pressed powder or foil with alternating layers of silicon stuck in a metal body up to 200 psi of deuterium gas placed over it to hydride the plating, and then it was pulsed. I actually have a picture of the components of the cell. Here's the contact, the electrical leads. The O-ring is so that when the flow through mode, the flow goes through the contact, not around the edges. We'll walk through the experimental. The protocol is simply to just load this into the cell, take it off somewhere, either on the counter, or occasionally just on the dash. Give it a short pulse, 200 microseconds, typical. Duty cycle of about 2% voltages and currents of range, and that is one of the problems, one of the reasons everyone has talked about. We've gone a little bit away from these powder cells. It is difficult to fabricate identical cells. Each one is different. This is some data off of some cells that run in the motor. We ran them off somewhere, brought them back, and took alcohols off of the cell. Cell 18 and cell in blue was interesting. Tom was off trying some things, thought he would expose the plating to sulfur, so he heated some sulfur and covered the surface of the plating with sulfur. And that cell did absolutely nothing. The 60 nanometers you're looking at is the result of using, in these early experiments, deuterium that had a concentration of 20 nanometers per unit. If you blow this blue one up, you actually can see the effects of separation. The early ones, deuterium will rise, and this last one was a deficit in the amount of deuterium, which is about what you'd expect. Cell 19 was an average producer, but cell 20 was really a pretty good tritium producer. One of the things of interest is that the tritium seems to be coming more from the palladium, not to decompose the palladium, either just by reducing the pressure or later on out here by heating. These are the results of some of the cells where we started to flow the gas through. The bottom line is just deuterium circulating around the loop to take a look at the drift. There is an increase in the drift weight, the drift rate. Cell 41 is essentially a blank cell loaded in just chunks of palladium and equivalent amounts of what we would have in a normal cell, highlighted and circulated. The effect, we believe, is due to the water form when you hydride the palladium. It does a better job of going around and cleaning out any residual that's been left in that cell from previous runs. Cell 42, on the other hand, was a fairly healthy producer of tritium. While we pulsed it, looking back on this, I'm not sure at the rate it's producing why we turned it off. One of the interesting parts of this is here at the end, you see the jump out. That's where we turned on the heat and dehydrated the cell. If you follow that up, the partial pressure of tritium, as measured by the ion chamber, follows the total pressure of the system. So the tritium is definitely there in the gas. This particular cell was reasonably interesting. Shortly after the ones I showed you before. Again, there's a deuterium background shown here. And then the blue is actually run afterwards, so I'll come back to it. But the red cell, the time that we were pulsing the cell was actually from this point to this point. At this point, we heated the cell, that's to get this short pulse and then a negative pulse. That's the effect we usually see with water, is to drive the cell negative at first. Then we held the cell at 150 degrees and simply let the gas circulate around the cell over a long period of time, tritium output from this cell. This blue cell actually runs with hydrogen, where we load up a cell with just junk hydride circulating around the cell, pump it out. We use that to try to clean the cell. And these runs follow this particular run. And it took, this is probably the 5th or 6th run with this to clean these out. But what it shows is this is more typical of just water when you expose the loop to water. A negative pulse, back up to high pulse, but it does return back to the baseline. Partly because of the difficulty you have producing these pressure powder cells, I shouldn't say that you have. Tom does most of the pressing of powders, so he has the difficulty and gets to cussing the point about trying to make them reproducible. But also because of an increase by us and among other people, interest that the effect may be due to current density. In many of the cells that were successful, we see things like this, these little arcing pits. That obviously would sometimes bring the experiment with high current density to a very small area as opposed to spread out over the whole cell. I'm not used to this team audience, and it nerves me that everyone's so quiet. Must be close to the break. Everybody needs a cup of coffee. I thought this was appropriate. Cold fusion is a paradigm. Well, gee, we're already right in there with the right buzzwords. But this view graph shows where we were headed during the last year. We went from trying to push current through plates to really trying to localize the current. Obviously, one of the easiest ways is to just use a wire. So I'll show you a picture of the cell. And we used actually a variety of diameters of wire around that. They're very long, wind them around an anvil. It has several effects. One, it localizes the current. Two, it reduces the amount of palladium, which obviously then reduces the amount of water that you introduce into the loop. It gets rid of that, at least it reduces that. effect, if not eliminates it. Even better is we can fabricate them faster and to some degree more uniformly. Here's a picture of the spool. The wire simply comes in, it's held by this down track on the end, is held, and then it's wound around many windings. Talk about first the wire, but then I'll come back, and since it's here, I'll show the powder track. We actually press powder into this track, palladium powder, covered with a Teflon filter paper, and then a block of Teflon that's held together to hold the powder into the track. This is a picture of the cells. It's not real visible. This is before you run, this is after. I don't know if you can notice that some of the wires have lifted off and moved up out of the track. We do believe that certainly during the heating, probably with the high driving, there's thermal expansion. One of the problems you have is the wire touching the main cord as it's sticking out in the air. It's in this pulsing mode. As you heat it up, how fast does it cool down? And what is its average temperature? This is the powder track again before and after. This particular cell is the one I'll show. Most of this damage literally was done at the very end when I cranked the voltage up real high just to see what it would do. We got some marking and burning. We ran this first wire sample we started before Christmas last year, so we thought this was a Christmas present. It turned into work pretty well. It's a Johnson & Matthey wire, and 13918 is the batch. Unfortunately, we didn't have a lot of them. As we'll talk about later, we were attempting to find some wire that would perhaps match it. It's a very clean wire, very low amounts of impurities. Later on, I'll come back to that. I believe that's one of the keys. It ran at a very low current density. Actually, over the Christmas holidays, nobody was there doing it with it, so we just let it run. After we came back, we cranked up the current pulses, because the pulses not DC current. It's DC current for a very short period, I guess. Cranked it up to 3 amps. And ran that while again, cranked it up to 5 amps and 6 amps. And at this point, turned the current off. So we were very enthused about these results. And it certainly seemed to validate our assumptions on current density. If you look at the tritium production rate versus current density, it makes a pretty reasonable plot. Besides hydrating, dehydrating, and heating the wire, obviously getting the wire hot enough. It's a picture of that same wire before and after. And to check, make sure you can see the same things that I said. You can see that this wire is recrystallized after the experiment. We went through a series of wires that occasionally the manufacturers claimed they were very pure. Some didn't even bother to make that claim and admitted they were fairly dirty. But even the ones that claimed they were fairly pure turned out to have fairly significant amounts of impurities in them. Until several months ago, we think we may have stumbled on another wire. And we don't have a complete analysis of this, but the initial indications are that it indeed is good fellow wire. It's fairly pure. Before I get to that, I have several different plots. We were running some Johnson & Matthey wire trying to look at the effect of current density. We're pushing essentially the same currents through 2 different diameter wires. And did not see much difference. This difference over here at the beginning is when we add the gas. This is without, when we increase the gas pressure in the cell, it causes these jumps. You can see that at the end of the cell, we bring it back to approximately the same number. There was actually a slight increase in the tritium production rate when we turn the current on. But if you look at the scale, it's a lot smaller than the wire I showed you before. That's difficult to believe. But the thing that is encouraging, this is the Goodfellow wire. The discouraging part is we got it turned on, ran for only about 24 hours on a Friday extending into a Saturday. And Los Alamos got its first snowstorm of the year and knocked out all the power. And took down the whole experiment, including we have not gotten our circulation pump back up. We do have the cell closed up, it's pulsing. We don't have access to it at this point to see if it's doing anything. We did for a short period right after we got power the next week. And we were able to obtain a little bit of data. But this Goodfellow wire looks very promising to us. We didn't really run 16 powder track wires. We just numbered all the wires sequentially. Here's an example of three. We didn't have tremendous success with them. They, like the powder cells, are somewhat difficult to build today. If you're trying to shoot to give yourself a resistance of 50 ohms or something, it's very difficult. And after you run them, you can see after we took it apart, we had some difficulties blowing the powder out of the track. But we did get some interesting results with cell 16. At this point, we raised the voltage. We got a spike, which I think was primarily noise on the chamber because we were getting a lot of electrical noise. But when this is actually fractions of an hour. It's not quite as brief as it appears to be. And we're taking data every minute, so it's quite a few data points in there. It did settle down at a considerably higher number. Whether something happened in there or not, I don't know. What's more interesting is this event over here. We raised the voltage up to 2 kilovolts. At this point, the cell was fairly high resistance. And it went along for a brief period. I happened to be watching this one. And, at this point, we started to get halfway, about a quarter way through the pulse, the voltage would drop, and we were able to push a fair amount of current through the cell. And this lasted. At that point, the tritium ring, this is one of the largest rates of tritium increase we've ever seen. It started. I was still there when that argument or whatever that effect was stopped. And immediately the tritium production just flattened out. So with that 6-hour period of time, there was a tremendous tritium production rate. This is what I referred to earlier. We decided, well, 2,000 was good, we tried 3,000 and essentially burned out the cell and run it. And finally, we tried a couple of different plasma cells. In this one, there's a 10 mil palladium foil. On the other side, some palladium wires that stick out. Again, we had gas inlet and outlet to hook this up to look for tritium production as we were pulsing. I hope that red line is visible. That's the expected tritium concentration. There are a lot of changes on this view graph when we change the pressure, so we know where the tritium level should go. The red line moves like this. Down in this region, fairly low pressure, I guess between these two times, we had a plasma discharge set up, and we really did not see much effect. When we increased the pressure, we had to turn up the and then decreased, we increased to 7 and back to 400 torque. And increased the voltage trying to get the plasma starting again. What we actually got was arcing. And during this period, we had significant arcing. It's during this period that we believe there was an increase in the amount of tritium. At this point, we raised the pressure back up to 700 torque. And this same delta that's produced here shows up. I don't believe there was anything happening during the rest of that. second plasma cell slightly different with a palladium plug instead of the wires and the palladium foil. We were certainly able to make that arc, but it was a pretty mellow cell. It did not do very much. Down here at low pressures, there's an offset on the tritium monitor. We used to re-zero it periodically. That gave us shifts that somebody, if we were not careful to note that. Now we don't touch it. We just accept whatever the zero is. But it was a very well produced. This is the first cell I showed you compressed. So the tritium production was right in that region. We do plan to do some more. These were fairly recent. We haven't had a lot of experience with them. Try to wrap up here. We did spend some time looking for gammas in our material. We very little bit spent some time looking for real-time gammas out of the experiments, but not at the time that we had been doing the producers. We looked at the palladium. Jack Parker from Los Alamos has looked at a lot of that and have not seen any. If you believe that the neutron to tritium ratio is 10 to the minus 8th or lower, calculate the number of tritium atoms and how many neutrons that would give you over the course of several hundred hours, it's going to be difficult for us to see that neutron rate over the background. We are going to continue with the wire powder water cells. We think they're very promising cells. We believe that the tritium output very much depends on the surface and bulk impurities based on our experience with the Johnson-Matthey and the Goodfellow wire. And at least that brief experience in the cell that was arcing, the plasma cell, was an indication to us that we were producing tritium. This last one, heating, the presence of a large current is critical. It's actually difficult to separate those two. It is the large current that causes the heating. We don't know which effect it is, whether it's the rapid heating and then cooling, or the large current. That's where the difference in the wire, whether it's setting out the main course, so that it cools rapidly, or it's sitting out, if it's lifted up and it's sitting out in the material, it's going to cool at a much slower rate after this 200 microsecond pulse. And assuming we don't get pulled off to do other things in our research funding, this is what we'd like to do in the next year. We'd like to continue to investigate the current density effects, also the bulk and surface impurity effects. We have added to our chamber a single slab, I think it's 7 helium 3 neutron tubes. It's not a real high efficiency detector, and a gamma detector. It is difficult frequently to run for months and get a cell that works very, very well. Rather than wait, try to then take that back somewhere, we'd like to start to look all the time. So when something occurs, we try to correlate with the increase in neutron and gamma rays. And we'd like to continue our collaboration with BYU. Stuart Taylor will talk about some neutron results they got with these cells up at BYU back in their time. Thank you.
I have two questions. One is, when you did arcing to observe the tritium, what was voltage you were using?
When we heat up to dehydrate the tritium,
So just heating up? No.
when we're pulsing it, that varies depending on the resistance of the cell, a few hundred volts up to a couple thousand volts.
The second question is, you showed cell 20, and it had 140 nanocubic. Is that old data or new data you're showing us?
That is old.
And
palladium silicon cells that I showed earlier were probably have all been reported on the previous 2 meetings. We ran a few of those over the last year, but without terribly significant results. We've really moved on more to the wire. I have a question.
In the experiment where you're using the Johnson-Matthey wire, what range of where the wire recrystallized, what range of temperatures were experienced by that wire? Do you know? The reason I ask is that in some of the very early palladium that we had returned to Johnson-Matthey by Fleischmann and Bonds, we observed recrystallization characteristic of temperatures having been generated in the electrode of between 200 and 300 degrees centigrade. I wondered what actual ambient temperatures did the wire experience, and have you shown the wire to a metallurgist, because metallurgists have a way of telling what temperature has been experienced in the wire.
The first part is I don't know what the temperature is. It heats up very rapidly during this 100 microsecond pulse with a lot of current, and then cools. So I don't know what the peak temperature during that pulse is. Did the metallurgist give us any data? You can speak now.
No, but all the wire that we looked at is recrystallized, and I think the temperature is the hottest when we dehydrate it. So we run a DC current through it, we may get it up to 300 degrees C. At that point, that may be good enough to recrystallize it. So I'm not sure there's any magic to having it being pulsed, but they're at the end of the run, to get all the hydrogen out, we do dehydrate it. I'd like to talk to you a little bit further about the impurities.
Yes.
On this part of your talk, you may have already said this, but I wanted to know if you knew the exact beryllium content of your palladium. The reason I ask is that as you look at the periodic table of isotopes, the only exothermic reaction that makes tritium, deuterium, is beryllium-9 and perhaps carbon-13 and oxygen-17. I wondered if you knew precisely what the content of beryllium is in that palladium.
Yeah, that'd be great. Yeah, I think I need number 11. We did analyze it with beryllium, and across here it's less than 1 part per billion in all the samples. Trust me.
Okay. Did you make a vacuum degaussing of all the wire before treatment at high temperatures behind the cabinet?
I'm sorry, try that again.
Okay. Did you make vacuum degaussing of the palladium wire before experiments? Vacuum degaussing at high temperatures?
Not at high temperatures, no. At moderate, very low temperatures.
Okay, please, thanks.
Is the significant production of tritium always associated with arcing, or did you see some tritium production in the absence of arcing?
In the Johnson-Matthey wire, I don't believe, in the wire samples, certainly I don't believe it was arcing. In the plasma cells, yes. And in the powder wire, it's not clear that's what was happening during that. Probably arcing, when the voltage was dropping, we were running a fairly high current.
I showed a physicist that specializes in switching phenomena, a fellow at Emory, the circuit that you had when you were using the palladium silicon discs. And he was talking about a phenomenon that switching physicists are familiar with that can double and quadruple and sometimes by a factor of 8 increase voltage due to some phenomena that I didn't quite understand associated with switching, which would bring your 3 keV pulses possibly up into the 20 keV range. The question I had, do you have any way of measuring what your pulse voltage really is?
We measure the pulse voltage. What you don't know as it goes through the palladium silicon cells is the individual, at any individual surface, obviously things are changing. When you press those together, there are variations to the surface, so it's touching at some place.
Is there any way to get an idea what the maximum voltage might have been on some of the arcs?
I don't know about the maximum voltage, but if the question is leading to the point of hot fusion, I think the best way is probably to look for neutron production in an area where we certainly know that the neutron to deuterium ratio ought to be 1 to 1. We get 10 to the 10th neutrons out, and we'll be able to see that easily. That's part of this. We're going to look at the neutrons and the ions constantly now among ourselves.
All right, I'd like to thank Dale again. Let's try and come back at about 10:45. For this remainder of the morning, we have Chris Will. We'll be talking to us about tritium generation and palladium cathodes with high deuterium loading during heavy water electrolysis. Chris.
Thank you, Tom. Good morning, ladies and gentlemen. We would like to discuss today results we have obtained some time ago. There was a new insights gained and added molecules data on tritium generation of palladium cathodes after they had obtained high earnings with deuterium. This group was performed at the University of Utah at the China National Fusion Institute in Salt Lake City. And I'm sad to say that Dr. Zizinska could not make it today. I'm sure she would enjoy her being here. It was in March '89 when Freshman Collins announced that electrochemically induced nuclear fusion would take place in palladium at around room temperature. In addition to reporting on XSC generation of the order of 10 months per cc of palladium, they also reported on the finding of tritium of between 1 to 2 times 10 to the 4 atoms per second, or a yield of about 3 to 6 times 10 to the 8 atoms per square centimeter per palladium. Later, figures between 4 times 10 to the 9th and as high as 1 times 10 to the 15th atoms per square centimeter yields were reported by 8 other groups. Notice, however, that we are talking about almost a million factor difference between the findings of various groups. In most cases, open cells were used, and in fact, very few H2O controls were run. We decided that it would be very important to run a large number of controls in order to get a firm idea as to whether the tritium indeed would come from reactions involving the heavy water, or whether they might come from cell construction materials, catalysts used in the cell, and what have you. Now, I'm listing here a partial list of reactions that can produce tritium. The list could be just as well twice and 3 times as long. Let me also point out that the tritium decay, and this was mentioned by one of the previous speakers, has a 12.3 years half-life, produces beta antineutrinos, and has an endpoint energy of 18.6 kV, which we will make use of later on when we discuss the spectra we obtained. Here is a long list of the steps that we took in our experimental procedure. We always ran, in fact, an H2O controlled cell in an electrical series and simultaneously to each D2O cell. Typically, at any given time, we were running 2 such cells, one heavy water cell and one light water cell in an electrical series. In some cases, we were running as many as 4 cells at the same time, but only 2 belonged to the electrical series. So these were 2 pairs of 2 cells each. We used those cells systematically, always with internal H2O2 gas recombination such that the recombined water was easily driven back into the cell electrolyte. Hence, and this is a very important point, we are not concerned at all with separation effects between tritium and deuterium. We also determine continuously during the experiments the H2PD or D2PD loading ratio, and I will say a few words in a moment about this. Palladium electrodes in the study that I'm reporting here today on were cut from the same spool of 2mm wire. I am making a point of this, and we'll come back to this very important point again later in this discussion. We did palladize, meaning we provided the palladium electrodes systematically with a palladium black layer of about 1 micrometer thickness. Let me say quickly that the amount of chemabsorption of hydrogen and deuterium in this thin layer of palladium black is absolutely negligible with respect to the amount of deuterium absorbed or included by the palladium. We used, and this may be somewhat thin to see here, cyclic loading and unloading to attain deuterium to palladium as well as hydrogen to deuterium ratios very close to 1. That means essentially 1 plus minus 0.05, which is incidentally the accuracy of our technique. Tritium analysis was performed on the electrolyte, the deuterium fill gas in the headspace of the cell, and the palladium pieces adjacent to the electrodes before an experiment. Since we are using a destructive technique, namely an acid digestion technique, to determine the tritium in the palladium, we could not very well use the palladium that we were actually using in the electrodes. So the best thing we could do under those circumstances is to try to cut from the same spool the pieces adjacent to the electrode and analyze those 2 pieces up and the whole part adjacent to the electrode for tritium. Tritium analysis was then performed on the electrolyte, the deuterium gas in the headspace, and the palladium electrodes, in this case after an experiment. So that we did essentially what amounts to a total measurement of tritium before and after the experiment, with the adjustment however that indeed we did not know whether or not there might have been tritium contamination in the palladium pieces that went into the electrodes. Tritium analysis of a large number, therefore, of as manufactured palladium pieces was done in order to create a large statistical base to see whether we could ever in these cases find Now to the experimental conditions. We used a closed two-compartment cell, employing, and this is an important point, a different electrolyte that most everybody else has used. Instead of LiOD or LiOH, we were using acid electrolytes. We used ambient pressure, hydrogen or deuterium, in a pre-evacuated headspace above the electrolyte. And that alone is an indication that our cells were pretty well sealed. However, there was a rubber septum that allowed us to withdraw electrolyte samples into one single cell. And one cell out of four we did this kind of electrolyte sampling, whereas the cells remain untouched in the three other cases. In the study reported on here today, we were using 2 millimeter diameter electrodes of typically 2 centimeter length, manufactured by Hoover and Strong, with a rather modest commercial type of purity, namely 99.9%. We did perform other experiments not reported here today on 4/9 pure material produced by Johnson Matthey, and also in some cases by a third manufacturer. We were using controlled current analysis, electrolysis, at quite low current densities, namely only between 5 and 20 milligrams per square centimeter. We had our reasons for that. We noticed that when we went to larger current densities, we could not obtain reproducibly voting ratios of 1. We did on some occasions go afterwards, after we had obtained voting ratios of 1, to go to current densities, in some cases as high as 1 amp per square centimeter. We used the control temperature in water mass of 27 plus minus typically 500ths of a degree centigrade. Our method for determining the loading ratios was a volumetric method developed originally as early as 1953 by Carnot and Muller, described as unshift electrochemie, and further later on sophisticated, in fact, at the National Cold Fusion Institute by Andy Riley. That allows them to come to an accuracy in the determination of the utilization for deuterium to the extent of 0.05 in the loading ratio. As I mentioned earlier, we used a closed system, and I haven't mentioned earlier. We have described in the literature in the previous talks that is a core or a closed system protein analysis system using a Beckman 5000 liquid scintillation counter with a sensitivity amounting to 1 × 10⁷ tritium atoms. Very quickly, a schematic drawing of the electrolysis cell. This is the sample report. That was the 3 cells not used with a lower septum. The 2 compartments are created by the fact that we are surrounding the central palladium cathode with a cylindrical fritted glass cylinder, and the platinum cylinder constitutes the platinum anode, which surrounds in a concentric fashion the palladium central electrode. The electrolyte level is chosen such that it goes higher indeed than the porous gas cylinder in order to cut down on the possibility of the gases communicating with each other rapidly. The headspaces above the analyte and catholyte are joined by this exterior loop. A catalyst comprised of a fuel cell electrode made by Linear Incorporated is a cylindrical piece that is mounted above the analyte. Incidentally, a similar cell design in its principles was used in Prague in India. Here is a preview and summary of the results obtained. First, to the question of loading. When being continuously loaded to 1 or 2 millimeter diameter palladium with a constant current, we obtain typically loading ratios of about 0.7. A quite nice statistical evaluation of the success or non-success of getting to high loading ratios by using continuous loading was done again in our institute by Andy and his associates on as many as 60 electrodes. In about 15% of those cases, loading ratios of 1 and sometimes exceeding 1 were attained, whereas in the vast majority, 2/3 of the cases, the loading ratio was 0.7. Sporadically, that group with their 60 electrodes found that the continuous loading got to values of the left-hand side. We found that if one cyclically loads, then partially unloads the electrode, trying to be careful that in most cases we didn't get much lower than 0.7, in order to minimize the cold yield produced by loading and unloading. We found that when we stayed at low current densities, we could always get to loading ratios of about 1. And that, however, once the technique had been developed for 16 out of the last 16 electrodes that we were found. We did, however, in every one of these cases, hybridized the electrodes, and we gas-free loaded the electrodes by subjecting the electrodes to a vacuum system to 1 atmosphere of hydrogen deuterium, which resulted, as usual, in a loading of 0.7. The manipulations on the electrode after gas loading were limited typically to the order of about 3 minutes. In these 3 minutes, one can easily calculate with the non-fusion coefficients how much material could have at maximum loss, and that loss could have amounted somewhere to about 5 to 7% of the material hydrogen loading. So we started in many cases, in most cases, with gas-free loading factors already of 0.6 to 0.7 before electrolysis even started. And here is a very typical loading curve for hydrogen as well as deuterium, particle loading ratio here against time. For continuous loading, in this case, at a current density of 50 milliamps per square centimeter. The initial slope is, of course, trivial and reflects simply the loading current. You notice at the time that one needs in order to get up to the typical loading ratios of 2/3 is at the order of 100 to 150 minutes. And dividing this group in our institute produced figures that are almost identical to these in a great variety of current densities and diameter levels. If one however applies the cyclic loading technique, we have the complex steps that we apply are shown down here. Then one notices, either that we do at time 0, meaning at the time of the start of the electrolysis, we start already with a loading ratio of 0.67 or 0.68, and that's pre-loading. That with every loading and unloading and subsequent loading, one gets typically a little bit higher than loading ratio. Until, in most cases shown, we get to loading ratios just under 1, maybe about 0.95, 0.96 or so. That, in fact, was the significant finding as shown here on electrodes. However, in the also 1 palladium, 5% lithium electrode that was produced by our metallurgy group at the University of Utah in heavy water cells showing in tritium ether. There are a lot of numbers that show the data that we obtained on these 4 200 strong electrodes. Let me just point out the time of electrolysis counted from the time on that we obtained loading ratio of 0.8. The significance of 0.8 is clear to many of us. We have observed in separate experiments that no tritium had been formed when the loading ratio was lower than 0.8, and it appeared that 0.8 indeed has a critical threshold value above which only we were able to generate tritium electrodes. The electrolytes are given in every single case D2SO4 and H2SO4 with the exception of seldom and one will be added with sulfate. The loading ratios in every single case are given. There is one that falls slightly outside, or so slightly outside what we got and calculated to be our accuracy. It is very close to 1 or 1. In every case, we give the atoms of tritium in the electrolyte, in the palladium metal, and in the gas before and after the experiment. And now these numbers may show up a little bit small in the background in particular. So let us look at the bottom of the table in slightly enlarged fashion. We give here the total number of tritium atoms generated in every single case, and even not detected. So we never detected in the hydrogen cell any tritium in either the gas or the electrolyte or the palladium. I'm giving the enhancement factor, which is the amount of tritium in the cell in the 3 phases after and before the experiment. And you notice, with the exception of one case, enhancement factor is up to about 50. In this one case, we mistakenly used a tritium, taking more tritium than found electrolyte, which was noted only after the experiment was started. It is interesting to note that the yield is nevertheless pretty close to the yields obtained in the other cases. And here finally is the average tritium generation rate, starting again to count at the time. Here, the palladium had reached a loading ratio of 0.8, and we notice once again that the average tritium generation rates are relatively uniform and are of the order of 10 to the 5th atoms per square centimeter per second, which then corresponds to about 0.1 micrograms. Continue now on the summary of some of the other results of tritium generation. We carefully determined the tritium or palladium ratios in the palladium and found it to be 40 to 230 times larger than the electrolyte or gas. Now this is a very important finding, I think, because it shows us that these values are so much higher than the equilibrium separation factors would be. They will only be 0.2 to 0.4. In other words, what this means is that we have a situation where there is very much more tritium in the metal than either in the gas or in the electrolytes, and that can only mean that tritium was generated inside the palladium. Of course, as time goes on, that negative liquid, very low values in favor of metal. On the other hand, liquid to gas, we are getting in these cases pretty close to equilibrium. After an experiment, after any of these 4 experiments with electrolytes, we are left in a charged state, meaning the tritium was to a large extent still contained in the palladium electrodes. They were then cut into various pieces, namely the shaded pieces are the ones that were cut from the electrodes and analyzed for tritium. And this gave us the possibility to come out with an maximum distribution in some form at least, in these palladium electrodes. What we found is that more tritium usually was obtained in the center, near the center, than near the ends, you have been detected in this case of the electrodes. This, in our opinion, could mean one of 2 things. Either the ends didn't charge as effectively as the tritium, and hence the tritium generation here was smaller than near the center of the wires, or that tritium indeed was originally formed near the ends as much as the material, but had, of course, more of a chance to fuse out through the ends than away from the center. These are previous results we have obtained, which I want to show very quickly to indicate how many background samples were known. These are results all obtained on as-received palladium. In this case, we analyzed the total number of 45 palladium pieces under the plate, and we are given the decompositions per minute per milliliter, 25 with a standard deviation of 1.3. Here are 14 samples of the scintillation liquid, which is used in the scintillation method, and we found virtually the same background. So that we come to the conclusion that there was, given the accuracy of up to P, no tritium contamination of these 45 pieces of palladium. The same statement can be made for the tritium, for the non-tritium found in 90, no tritium found in 90 other pieces of palladium. They were used for a closed system to leak, whereas in the other table, an open system that only technique can be used. Now, very quickly to the question of the spectrum. We established first that the palladium pieces that have been used as electrodes, and that's the lower part of this graph. We plot the counts per minute to 5 channels against the channel number, and given them here almost illegible, I believe, the relationship between the channel number and the energy of KeV, the energy of the electrons in KeV, and it is 72 plus 280 times the volume of the KeV. The channel 400 is equivalent to 14.9 kV. Now this is the unknown. This here is a tritium standard, which was simply made by putting tritium into H2O with an activity of 1,000 ppm per milliliter. We notice that the maximum, as well as the intensity left in channel 400, but the two curves count each other very well. The same statement can be made with respect to a tritium standard supplied by Beckman, where once again the curves, when normalized, are essentially coincidence. The question arises, are there other data emitters that would produce curves, spectra, of the same shape and with the same cut-off energy? What we did is, and I appreciate the help of John Cassidy along these lines, what we did 210. Lead-210 has two beta emissions with 15 and 61 kV. That makes it possible to easily distinguish between lead-210 and tritium, and therefore can exclude lead-210. We found, however, that plutonium-241 has a color and an endpoint energy very close to that of tritium. We are presently still continuing to separate clearly the plutonium-241 possibilities of determining formally or from the spectra. Indications are that indeed this is possible, and the spectra are sufficiently different so that we can say that plutonium-241 is not the impurity or any impurity that would give rise to the spectra. Thank you. Now there a summary as to where we stand about the probability of the tritium that we find with the palladium after all experiments is due possibly to accidental contamination, a statement that of course has to be examined very closely. We contend that the tritium, or let's say the spectra that we find to ascribe to the presence of tritium can't have originated from the electrolyte in the first place, because if this were so, then we could not understand why the tritium to deuterium ratio of the palladium is 230 and 233 times larger than the tritium to the deuterium ratio in the electrolyte. In fact, we would get a situation if the electrolyte were contaminated with tritium originally and the palladium would have no tritium, we would have the opposite, namely, we would find an exceedingly small tritium to deuterium ratio, essentially close to zero, and just the opposite is being observed. We also contend that the tritium could not have originated with the palladium prior to the experiments. If that would have been the case, tritium could have started to accumulate in the electrolyte immediately should taken with a grain of salt. One calculates the fusion time needed for tritium contained in the palladium to get out and give the first signal within the sensitivity of particularly we calculate about half a day. In truth, what we find is that it takes about 2 days, namely at the time, to generate, to find any tritium in the electrolyte, and that coincides with the 2 days typically we need in order to create, to generate a level ratio of 0.8. Now let's for a moment think that we know nothing about statements 1 and 2. Let's forget these for a moment. Let's simply hold we look at the data being obtained and in a statistical way. And then we can calculate the probability that we pertain to picking all 4 tritium-containing palladium pieces from 17 pieces total. 17 is the number of pieces that we analyzed from the same spool that the 4 electrons came from. And that probability is under the assumption of a random tritium distribution, 1 in 130,000. So an exceedingly low probability would be that the tritium that we found in these 4 palladium electrodes was due to accidental tritium contamination. Concluding very quickly, we find low-level tritium generation. When I say low-level, it's well visible, about 100 times above background. The low level is compared to, let's say, heat levels at 1 watt. And unfortunately, only a certain type of palladium, where we can't at this moment say what makes that certain type of palladium. But we find no tritium at all in the same palladium from the same spool in 4 controlled cells. Tritium appears to be generated inside the palladium rather than at its surface. Tritium contamination of the arsenic palladium is unlikely. No tritium has been found in two other types of palladium, one of the Johnson-Matthey palladium, and another palladium with an electrode, in spite of the fact that we managed to lead to PD ratios of 1. Therefore, it seems to us that a loading ratio of 1 is a 1.8 is a necessary but not sufficient condition. Question obviously is what else in addition could it be? And we're thinking in terms of specific metallurgical properties and or impurities in the palladium that might make a difference. Part of this work has just appeared on the 30th of January. Thanks for your attention.
I'd like to ask one question first, and that is, did you see any specific difference between the Google Strong and Johnson Matthey in impurity content or position that you see?
I'm sorry, ask the question again, please.
That was there any discernible difference in Google Strong versus the Johnson Matthey impurity?
Along which lines? Differences along which lines?
Metallurgical or impurity content?
We did not, as part of this particular study, make any detailed study of the metallurgy of these two lawyers. We did have performed analysis of these two lawyers. The impurity contents were, as you might expect, different. We may have found 10. These were differences that were noticeable. Beyond that, when it comes to metallurgical properties such as preferred orientations, texture, the hardness of the wire, we did not make a final study of that process.
Please, have you evidence on the release of the tritium by relaxing the polarity on the geoelectric?
I have a
Have you evidence on the release of the tritium by relaxing the polarity of the cell?
Yes, absolutely. We are getting down typically from whatever the loading ratio was at the end of the charging cycle to typically values of 0.5 to 0.6, sometimes to 0.7.
Professor Barker.
Make 3 points that you actually made up. The first is that I think it should be pointed out that you're probably the only person who's used the assay. Type research in sodium hydroxide, most people use lithium. I think that's rather important because there's a strong concentration of lithium and sodium in each other. The new hydroxide under the situation that cannot be a factor. Most important. Secondly, I've noticed too, in analogy to what movement strong, the less pure palladium produces tritium. It's not good to be very pure palladium if you want to get tritium. And thirdly, you gave specific rates, 10 to 5 grams per square centimeter second and so on. We made a study of the dependence of tritium production on the potential of the electrode, looked at electrochemically as a load potential, and plotted the off rate against eta, load potential. We found about 0.2 for a so-called chance of slope with regard to tritium generations of current. In short, the rate of the circuit must be controlled by a surface process because of this type 9. And I think one shouldn't stress too much that this rate is the rate of production of tritium. It depends on least over 3 to 4 orders of magnitude.
I will try to be very short. I couldn't agree more with you that you emphasize once again the significance is a significant difference. In one case,